Yeah,
Okay.
and Adway, so I suggest, yesterday we had some additional questions. So I'll just post one question and then we can start. Is that okay, Gokhan?
Yeah, sure.
Sure, sure. Please
Oh,
go ahead.
perfect. So there was a question from Legend. This is about the ensemble numbers. How do you balance the ensemble numbers? So the question was when designing experiments like whether it's high-res MAP or standard historical runs or simulations, how do we decide how many ensemble members to actually produce? Is that mainly driven by computational constraints, community needs, or other scientific priorities? And he's just curious how you balance these factors on the production side.
Well, the answer is pretty much all of the above. And it primarily depends upon your scientific question and what field actually, or what fields you are interested in analyzing. So for precipitation, for example, more ensemble members, I believe, is better. And when we ran the CSM2 large ensembles, we simply went for 100 ensemble members, but that was what we could afford also. I mean, we had the computer resources that was in collaboration with what is it, IBS in Busan, South Korea. So they had the resources, and we just wanted to go with 100 ensemble members. But people can analyze any field that they want. And in some cases, I mean, there are studies, actually, it's in, I can't remember whether we put it in Rogers et al. 2022 paper. For some fields, 10 or 15 ensemble members might be okay.
Right.
In some cases, for Pacific variability, for example, in the North Pacific, you may need 35 to 40. So it depends. It depends.
Right. Thanks a lot, Gogan. So let's start with today's session. Today, yesterday we had an overview from Gokan on air system modeling, the history of it, the challenges with it, the status and future of air system modeling. So now we get into more into the detailed aspects of it, particularly the ocean part of it. Uh, the floor is yours, Gokan. Thank you
Thank you
for your
very
time.
Thank you, and good morning, everybody. And so, as Roxy indicated, this morning and tomorrow morning, I'll be focusing on ocean modeling and some of the details related to ocean modeling. So today, I'll try to cover, so this is a two-part talk. In part one, today, I'll be talking about ocean modeling challenges and properties, ocean properties. I'll briefly show a few governing equations and approximations used in ocean modeling. I'll then show some examples of discretizations, and this will be both temporal and spatial discretizations. Then I'll touch upon vertical coordinates in ocean modeling and show some grid examples. Tomorrow, so in a sense, this is in the atmospheric sort of modeling sense. I'll be talking more on the dynamical core side for ocean models. And tomorrow I'll be talking about some of the what I consider important parameterizations used in ocean modeling. So with that, some of the ocean modeling challenges. One of the major challenges in ocean modeling is the representation of bathymetry or bottom topography. This is showing the global bottom topography. And as you can see from this plot, the bottom topography or bathymetry is very highly irregular in ocean modeling. You can see quite a lot of, so this is the ridge, mid-Atlantic ridge. So you can see examples of ridges. You can see many, many islands. You can see a really complex topography with really narrow channels. This is a blow-up of the North Atlantic. This is one of the sort of important regions for the Atlantic meridional overturning circulation or thermohaline circulation. And you have seen probably lots of news articles, especially over the last several years, whether AMOC is going to collapse or not. And it is this area is actually quite important, the representation of bottom topography in particular. For example, there's the Denmark Strait overflow here, and there's the Farabank Channel overflow. And these are extremely narrow overflow regions, and they need to be properly represented, or as I'll talk about it tomorrow, they can be parameterized. You can see also the Charlie Gibbs fraction zone here. It's a very narrow zone that actually communicates, provides the communication between the eastern and western side of the Atlantic basin. And this is, again, a blow up of that region. So you can see the fracture zone here. And and then finally, I just wanted to also highlight what's happening in the Indian Ocean region and the maritime continent. You can see lots of shallow areas here, as well as a lot of islands. And it is a challenge in the ocean modeling, sort of to capture all of these flows properly. And there is no way on Earth that we can actually capture all those flows, flow properties, temperature and salinity properties correctly. So these are very challenging. Another interesting sort of thing is that representation of bottom topography or bathymetry in ocean modeling remains rather ad hoc, with each group or modeling center applying their own method, and there is really no accepted best practice to come up with the bottom topography. Processes, when I say processes in this case, how the bottom topography is obtained by a particular group, usually are not well documented. And once the bottom topography is created, it is usually used for many, many years. In fact, for POP2, for example, we are still using bottom topography that we created roughly 20 years ago. And the person or people who created those fields are no longer at NCAR, they retired or they left. So we don't really have a good sense of how the bottom topography was actually created. It also involves quite a bit of trial and error to obtain reasonable transports across various channels and straits. For example, in some cases, in Sea of Japan, this transport depends upon the cross-sectional area. In some cases, the Mozambique Channel transport actually depends on the model, sort of the channel depth. So these are all trial and error sort of determinations. And details matter. And I circled here, I don't know whether you guys are familiar with the bottom topography there. There is actually a passage called Samoa Passage. It actually communicates, or it provides a deep water flow pathway from the South Pacific into the North Pacific. And it is extremely narrow. And if you do not properly represent it, then essentially you will not get much ventilation in the deep Pacific Ocean. So again, these are, when we create the bottom topography, we do a lot of hand editing. Continental boundaries, whether a part should be a sea or a land, is essentially a very tedious task. It takes a lot of time. Another aspect of the bottom topography is, I believe I showed this plot or movie yesterday. Land boundaries in the ocean exert strong control on ocean dynamics. And what I mean by that, essentially, you can see the presence of strong western boundary currents. In this case, it's the Crochet in the Pacific and the Gulf Stream and its extension, North Atlantic current, are clearly visible. And similarly, in the Southern Ocean, you can see the extensions of the western boundary currents, and essentially they are confined by topographic features. I'm not going in depth here, but you can see as you go, you can go deeper in the ocean, and you can see similar controls by topography of ocean currents. So this is just to show you that grid resolution makes a huge difference, and I'll be talking about the parameterizations tomorrow. What is shown here is just a southern tip of Africa and sea surface temperature distributions. On the left side, we have a snapshot, an instantaneous snapshot from our tenth of a degree, one of our tenth of a degree simulations. And on the right side, it is the sea surface temperature distribution. Again, this is a snapshot, but it doesn't look like a snapshot, but it is a snapshot. And it is from our workhorse 1 degree simulation. So you can see that there is quite a bit of difference and mixing associated with subgrid scale turbulence, that all of these features somehow need to be parameterized in ocean modeling. So this is essentially indicating that grid resolution is quite important. And usually the length scale associated with these mesoscale eddies is the Rossby deformation radius. And this is talking about that. So the density, in contrast with the atmospheric model, the density change from top to bottom is a lot smaller in the ocean. And with respect to the surface, sigma zero density, literally the density change is of the order of 0.02 or 0.03 grams per centimeter cube. So it is rather small. When that is small, the corresponding Rossby deformation radius given by this equation here, n is the buoyancy frequency, pi is pi, f is the Coriolis parameter, and h is a length scale, usually the vertical depth of the ocean. The Rossby deformation radius is of the order of hundreds to tens of kilometers. This is the plot here is from a paper by Bob Holberg, in which actually he presented sort of the grid resolution required to resolve baroclinic deformation radius. And I wanted to stress here that when people use the term resolve, it is usually used in a really loose way. In this case, by resolving, it is meant that you have at least 2 grid points within one Rossby deformation radius. But it doesn't mean just by 2 grid points that you are going to essentially resolve a full sort of representation of a mesoscale eddy. I mean, if you're coming from computational fluid dynamics background, you will have learned that you need maybe 4 to 8 grid points to resolve something. So this is clearly far from resolving mesoscale eddies. Initially, like 20 years ago or something, when people went to higher resolution, they said they were resolving mesoscale eddies, but now it is mostly referred to as eddy permitting or eddy allowing resolutions. The point that I wanted to make here is that at low latitudes, indeed, order 1 degree resolution, you can see it in the color scale, might be enough to have some sort of reasonable representation of eddies, mesoscale eddies. But as you go to higher latitudes, you can see that as the Rossby deformation radius gets smaller, then you need more grid points to resolve or to represent maybe in a better way mesoscale eddy. So this is a major challenge in the ocean modeling community as well. Equilibration timescale is another important consideration. In the ocean, mixing across density surfaces is extremely small. That's the interior dipycnal mixing. Once water masses are buried below the mixed layer base. If you do a simple back of the envelope diffusive timescale calculation, diffusion timescale is simply a vertical length scale squared divided by vertical diffusivity coefficient. On average, the ocean depth is about 3,500 meters, and that is below the, let's say, boundary layer depth or mixed layer depth. And if you essentially take a typical vertical diffusion value of 10 to minus 4 meters squared per second, then you'll get order 4,000 years as equilibration time. So these are rather long time scales. In order to reach equilibration or some kinds of quasi-equilibrium state, you need to run the ocean model for a long time. This, of course, this analysis, back of the envelope analysis, ignores tidal mixing. And I'll talk about that thing tomorrow. But tidal mixing can reduce this equilibration time simply because tidal mixing adds another diffusion diffusivity to this background diffusion value represented by K sub Bg here that'll increase this vertical diffusivity and in turn reduce the equilibration time somewhat. But you need to keep in mind that usually tidal mixing is associated with topographic features. So this is essentially not valid. Faster equilibration times with tidal mixing is not uniformly valid across the global ocean. So the bottom line for climate or Earth system model simulations for long term is that performing long equilibrium simulations are not really practical in ocean modeling, particularly at eddy resolving or permitting resolutions. And therefore, we must live with deep abyssal ocean not being at equilibrium in most simulations. So just to give you an idea about what I mean by these equilibration times, here I'm plotting global potential temperature profiles. So as a function of time. So the x-axis is time. This is a 1200-year simulation. And the upper ocean, upper 1200 meters, sort of is exaggerated to show more details. And these are simply globally averaged, horizontally averaged profiles. So you can see that as we integrate longer in time, there are still in the upper 500 meters and also at depth, the ocean is still warming. These are coming from fully coupled simulations. This is the global picture. And if you look at now individual basins, this is what's happening in the Atlantic. You can see that there is actually warming, significant warming at sort of intermediate depths, but they are not changing necessarily. There's not much of a trend. But if you go below that, at depth, below 2,000 meters roughly, ocean is actually showing a warming trend. So it's actually warming from 1.2 to 1.4 degrees. If you look at Pacific, now you can see that there are actually trends. In the upper ocean, in the upper 500 meters or so, it is warming, whereas at depth, it is actually showing again a warming trend, but it's actually initially it was a cold sort of temperature distribution. And finally, in the Southern Ocean, you can see again trends, particularly at depth, it is getting warmer. So this is 1200-year simulation, and you can see that there are still significant shuffling of water masses or temperature distributions or heat content going on, not only in the vertical, but also across ocean basins. Okay, so another property of the ocean is that, as I said, because of the weak interior mixing, you can actually follow water masses. When they form at the surface, they do not necessarily change much of their properties. They can get subducted in intermediate or deep layers with the same temperature and salinity sort of characteristics. And then in the ocean modeling, it is relatively common practice to show these temperature salinity plots, so-called TS plots. And then usually you see, in this case, sigma zero density, that's pressure is reference to the surface. These are the density contours. And when I say water masses sort of can be identified, this is what I mean here. This is, for example, NADW is the so-called North Atlantic deep water. And this is the Antarctic bottom water, AABW. You can see that they largely, essentially throughout time, or if you follow them, they preserve their temperature and salinity properties, and they pretty much have maintained their densities. The upper panel here, upper right panel, shows different water masses, and there are a lot of them, and this may not be showing all of them. You can see where they form with the surface fluxes or air sea interactions. I don't know whether you guys are familiar with the water mass formation or transformation, but these are essentially forming water masses through water mass transformation. And then the bottom right panel shows a zonal cut along the Atlantic basin. This is the North Atlantic here. This is South Atlantic. It is showing the silicate. Essentially, it's a passive tracer concentration. And then you can see how the silicate signature actually is reflecting water masses formed in certain places. For example, LSW stands for Labrador seawater. This is actually water formed here, and then you can see its signature. North Atlantic deep water, then it becomes North Atlantic deep water. You can see its signature going in here. And the densest waters in the Atlantic basin, or in the world for that matter, form actually in the Weddell and Ross seas. They are classified as Antarctic bottom waters, and you can see their signatures all the way in the ocean bottom. They penetrate northwards into the Pacific, and that's exactly what I was talking about when I mentioned the Samoa Passage. Ventilation of the, for example, deep Pacific is through the Antarctic bottom water. And you can see other water masses here. As and AAIW is another important water mass. That's the Antarctic intermediate water that essentially forms along the high southern latitudes. Some other properties of the ocean. The heat capacity of the ocean is much larger than the atmosphere. And this makes the oceans an important heat reservoir. An ocean, if I'm not mistaken, can hold the entire atmospheric heat content within the upper 10 meters or so. The ocean contains the memory of the climate system. This is also important. This is important implications for decadal prediction, or for that matter, interannual to decadal, multi-decadal prediction studies. Seawater does not change phase. We do not have gas form or anything. It just stays as liquid. However, when the temperatures go below freezing, including accounting for salinity content, we simply form ice. We warm the ocean accordingly, and then pass the formed ice to the sea ice model, and they keep track of its accumulation. The ocean density is a nonlinear and rather complicated function of temperature, salinity, and pressure. And if it is not treated properly, you need to be careful in its calculation, because it can be quite expensive to compute density in the ocean because it's a rather complicated nonlinear function. I just wanted to give you an idea about sort of early history of ocean modeling. I think we included this schematic. This is from Bert Sempner, who passed away several years ago. And it is included, I believe, in the manuscript that I mentioned about history of climate modeling. Essentially, the ocean modeling sort of in the world is starting with GFDL, Kirk Bryan and Cox model, going back to 1969 or late 1960s or early 1970s. And then this schematic is showing you essentially how that essentially the same pretty much dynamical core evolved through development by different institutions. So Naval Postgraduate School, this is in the US. Los Alamos National Lab, then they developed POP, which is essentially its parallel ocean program, but it is coming from MOM, which stands for Modular Ocean Model. There were some development efforts in UK. GFDL continued this development effort under MOM, as I said, and then at NCAR, we started in early 1990s with the NCAR Community Ocean Model, which was based on MOM, which then became the Climate System Model, which is the sort of predecessor of what we have here today in CESM. And then NEMO and other groups essentially, or other ocean modeling activities followed after this. There's also HICOM and a bunch of other ocean models. So usually there are three languages that I'm aware of used in ocean modeling. The standard, sort of the going back to many, many years, is Fortran. More recently, in fact, we are actually currently pursuing some C++ conversion of MOM6 code base to C++ for running more efficiently on GPU-based systems. So it's C++. In fact, Department of Energy is also developing a new ocean model completely written in C++. And there's also now Julia, which is developed at MIT. And if you are familiar with Oceananigans, the ocean model, which is based on the older version, which is a rewritten, a newer version of an ocean model based on MIT GCM. And my understanding is that I'm not familiar with Julia, but it's supposed to be both CPU and GPU friendly language. So switching gears to governing equations, we have basically 7 equations in 7 unknowns, 3 velocity components, 2 horizontal, 1 vertical, potential temperature, salinity, density, and pressure. And if we are interested in using ocean biogeochemistry, then for each of the passive tracers, we have 1 equation. And these can be, for example, CFCs and ideal age. For those of you who are not familiar with ideal age, it simply represents the age of a water parcel. It indicates how long ago it was last in contact with the surface. In other words, water parcel ages by 1 time step per time step. What approximations do we use in ocean modeling? So they are listed here. We use the hydrostatic approximation, which means that variations in density are considered to be too small to affect inertia, but are important in terms of affecting buoyancy. This simplifies the equation for the vertical velocity component. When vertical accelerations are small compared to the gravitational acceleration, the hydrostatic approximation is valid. However, when ocean becomes statistically unstable, meaning that the conditions are such that heavy water ends up sitting on top of lighter water, actually vertical overturning should occur, but it cannot occur because we don't have the vertical tendency included in the model. So that kind of mixing needs to be parameterized. So we just do it simply by increasing the vertical diffusivity or viscosity coefficients. We use the Busnesque approximation. That means density differences are not really important except for when they are multiplied by the gravitational acceleration. Therefore, the sound waves are ignored. We use continuity in incompressible form. That means seawater cannot deform, so what flows into a control volume must flow out. We have the thin shell approximation. This is similar to the atmosphere as well. The ocean depth is neglected compared to the Earth's radius. And together with horizontal motions being much, much greater than vertical motions, the thin shell approximation of the Coriolis force then results in retaining only the horizontal components due to horizontal motion. So this simplifies things. We assume that the Earth is spherical, so geopotential surfaces are assumed to be spheres. And we use turbulent closures, parameterizations. So subgrid scale processes can be parameterized in terms of the resolved large-scale fields and features. These are usually down gradient diffusion approximations, which I'll talk about tomorrow again. So this is 1 or 2 slides here, just showing you examples of governing equations. I'm not sure how many of you are familiar fully with the governing equations used in Earth system modeling. The top one is the zonal momentum equation. The next one is the meridional momentum equation. These are in spherical coordinates. And for simplicity, shorthand notation is used. In this case, L of alpha is, for example, is the advection operator in spherical coordinates. We have the viscous terms, zonal and meridional viscosity, given in F sub hx and F sub hy respectively. We have the divergence operator, it's del squared essentially, and we have the vertical viscosity operator shown here. The continuity equation is simply the advection operator. Hydrostatic equation is simply shown here as dp dz as minus rho g. Equation of state is nonlinear. It's just simplified or notation-wise shown here as a function. We have the active and passive tracers. They are simply given by conservation equations with horizontal diffusion and vertical diffusion terms shown here. This is, again, for simplicity, the horizontal diffusion or isopycnal diffusion coefficient is shown outside the del squared operator. In reality, in the model, it's inside. And then when I go back to these equations, they are written such that we actually preserve certain properties, such as solid body rotation. And all of those extra terms are added in the model equations. Boundary conditions. So at the surface, we have the momentum and tracer fluxes, and they are determined using bulk formulations. These are kinematic bulk formulations, plus we have the radiation components. And they come from either atmospheric data sets, or in fully coupled simulations, they can come from the other components, such as the atmosphere and sea ice. If the ocean model is volume conserving, then freshwater fluxes are converted to virtual salt fluxes. POP, that's the ocean model used in CSM2, is a volume conserving model, so therefore we use virtual salt fluxes. But MOM6 that we are using now in CSM3 can actually use true freshwater fluxes, so we don't have to convert things to virtual salt fluxes. For the bottom and lateral boundaries, we don't have tracer fluxes, meaning that we don't have heat or salt coming from the side boundaries. However, we allow for geothermal heating that's imposed as a bottom or lateral, well, it's bottom heat flux. It is about 100 milliwatts per meter squared. We do not allow flow into rocks, except for an overflow parameterization that I'm going to talk tomorrow. We usually use no slip flow boundary conditions on lateral boundaries. And for the bottom drag, we use sort of traditional quadratic bottom drag. This is an example for discretization. I'm not sure whether you are familiar with the various grids that are being used in modeling, not just ocean modeling, but also in other components. In POP, we use the Arakawa B grid, and I'm showing you how it's structured here. If you look at the grid, this is looking at it from the top view on the left side. So temperature, salinity, or other tracers are at this grid centers. And then the velocity components, horizontal velocity components, U and V, are at the corners of the cells. This is a T-grid cell. And if you look at it in the three-dimensional way, now temperature, salinity, and pressure are located at the center. This is right here, so this is center. And the velocities, horizontal velocity components are here at the edges, or at the corners of the cell, when you look at it from the top. There are two vertical velocity components, or fields. One of them is associated with tracers. That's at the top and bottom of the center of the grid. And then the other one is, I noted here as WU, it's associated with velocity components, and they are actually at the top and bottom of the velocity locations. And these are related to each other. We actually preserve continuity based on W, and at the tracer points, or the W associated with the tracers, but WU is an area weighted of average of the W at the T points. So Arakawa B grid naturally accommodates no-slip boundary conditions, and I'll show you the sort of better schematic for that thing on the next slide. It has better dispersion of Rossby waves at coarse resolutions in comparison to the C grid that I'm going to show in a second, and it has smaller truncation errors in the computation of the Coriolis terms. It has disadvantages also. It cannot represent single point channels, and I'll show you the example on the next slide. And there are larger truncation errors in the pressure gradient terms. So now this is showing a top view and side view of how we are discretizing things. So green areas are the land points, and then schematically shown here are the T points, and then U points. Those are the velocity points. So you can see that you cannot really have a single passageway, single grid point passageway, because in that case, there would not be any velocity. All the velocities would be zero because the velocities are located at the boundaries. So you must have a minimum of two grid points in this discretization approach to allow flows through passages. And this is from the side view now. You can see the ocean bottom here. And then similarly, again, U velocities are here. So you can just impose the no slip boundary condition at the sides easily, but you have to have two grid points for passageways. And then just if you want, this is also referred to as the U grid. If it is centered at, if it is centering a U point, then it's referred to as the U grid and shown here there. Okay. So another discretization is the Arakawa C grid. In this case, T is, or the passive tracers or temperature, salinity, and density are still at the center. But then now the velocity is, instead of being at the corners of the grid cell, U velocities, zonal velocities are here, and the meridional velocities are here. So you can see clear advantage of this thing, right? Divergence operator is you don't need any averages, you don't have to do anything. It's simply du, dx, and dv, dy. So it naturally represents the divergence operator. And that's what it means as an advantage here. Natural discretization for some fields allows single point channels. Disadvantages include Coriolis terms requires horizontal averaging, making the inertial gravity waves less accurate, and there are poorer dispersion properties for Rossby waves at coarse resolution in comparison to the B grid. This is used in MOM6. If you're interested in what is MPAS is the model for prediction across scales. It's using an unstructured grid. It's an hexagonal grid in this example. And it is various fields are located in different places over this schematic. So locations of the velocity points are shown by these squares. Locations of potential vorticity are shown here. They are at the corners. And locations of thickness points, meaning temperature, salinity, and all that stuff, they are actually at the grid central. So it's a bit more complicated, this discretization. Just to give you an example of how we discretize things, I don't want to go into too much detail here. Just as a simple example, the upper left is the horizontal view, and this is the vertical view of discretization. And I just put the simple horizontal advection discretization here. The idea on a B grid is, forgetting about all the details of the equations here, you end up essentially, if you want to compute an advection operator, zonal velocity multiplying a temperature, you compute everything here where my arrow is. I hope you can see it. And then you differentiate it from the corresponding value on the west side. And again, for the north and south, you essentially create an average of the velocities. You create an average of the temperatures. Similarly, average of the velocities for the south, and then average of the temperatures for the south, and then you create their difference. This is all it is doing. Similarly, you need some kind of averaging for temperature or the tracer quantity in the vertical as well. You need certain weights to preserve conservation of potential energy and kinetic energy conversion. And that's why these grid factors are coming into these equations. So it's not simple sort of central advection or discretization. Central advection is usually used for momentum. For tracers, we end up using, especially at coarse resolution, a scheme that does not create extreme values. And in POP2, we end up using third order upwind scheme for this purpose. An example of time discretization is shown here. POP2, for historical reasons, going all the way back to original versions of MOM, has been using leapfrog time stepping. This is essentially a 2 delta t scheme. In order to compute a variable at the new time level, you essentially advance it from the 2 time steps prior, And for stability reasons, advection needs to come from the current time step, and then the diffusion comes from the previous time level. And source terms, these are the forcing, can come from either the current or the previous time level. And this is sort of a schematic. And as you can see right away here, you can see with one of the big disadvantages of leapfrog scheme is it creates a split mode. If you do not essentially are not careful, then these modes are going to be independently evolving in time. So to prevent that, occasionally, and it happens to be every 17 time steps, these modes need to be sort of brought together either via a time averaging time step, or I incorporated a Robert filter time step in POP2, which is somewhat better sort of conservation properties and other properties than simple time averaging. Vertical coordinates. I would say the choice of a vertical coordinate system is one of the most important aspects of a model's design. And there are several vertical coordinate systems in use, and three of them are shown here. This is the Z coordinates, which is the usual level coordinate system. Sigma coordinates follow the bottom topography, as you can see here, and isopycnal coordinates are simply following the density structure. Each coordinate system has its advantages and disadvantages, and therefore many groups, including us now with MOM6, we end up using a hybrid coordinate system, which essentially blends the in the ocean interior isopycnal coordinates and in the near the surface with the Z coordinate level coordinate system. This is still a very much active research area. How your certain properties in the ocean model, for example, the overturning circulation, its depth and all that stuff can depend upon the properties or the details of the vertical coordinates. The newer generation of the ocean models tend to use the arbitrary Lagrangian Eulerian method in the vertical. It provides variety of options. When it is fully Eulerian, it reverts back to essentially a Z-coordinate system. When it is in a sense fully Lagrangian, you need remappings of the sort of vertical levels. Then the configuration is such that the mesh moves with the fluid rather than so there is no explicit transport in the vertical. You don't necessarily have a vertical velocity, but the mesh moves. And if you are in between, other vertical grid configurations are possible. In MOM6, we are using, as I said, hybrid, which is part of this ALE system, and MPAS is using a similar algorithm as well. There are versions of NEMO also using ALE method in the vertical. So just a few grid examples here. This is one of our grids that we use in coarse resolution models. We displace the pole into Greenland. We don't want to have it in the geographical location, otherwise we can't solve the equations. There's quite a bit of high grid resolution in the high latitudes. We also do for equatorial refinement. Even if our grid resolution is nominal 1 degree, near the equator, we end up using about 0.3 degree resolution. That's to better resolve the equatorial current structures. This is what we use in high resolution. We use actually a tripolar grid. We get better sort of aspect ratio of the grid by doing this approach. By using this approach in the Arctic, this is nominal 0.1 degree. And these are two grid examples from the MPAS unstructured grid options. You can see the cube sphere structure here. If you look at it carefully, there is the corner point where my arrow is. And then MPAS also gives you the option of sort of grid refinement within the whole system. But again, if you have a global model, if you refine the grid, you're essentially stuck with the CFL number criteria in terms of time stepping because you need to obey that thing, and that's dictated by the finest grid resolution that you have. So there is no free lunch. You have to pay the price somewhere.
Gokhan, we have about 5 minutes for Q&A. Yeah.
Sure, I'm almost done, I think. A common practice used in ocean modeling is the barotropic baroclinic split. Because of the CFL stability condition associated with fast surface gravity waves, we need to essentially use a separate algorithm or separate method for the barotropic mode. The barotropic velocities can be ordered 200 meters per second, but they don't impact climate. We don't really need to explicitly resolve them. And instead, we solve the barotropic equation implicitly, either using a truly implicit method or subcycling the time step. And fast-moving gravity waves thus are filtered out. But as I said, that's okay because they don't really impact climate. This is an example of a sort of coupling time stepping. We have the atmospheric model, coupler, and ocean. This is time from 1 to 12 hours. Atmosphere usually runs at the coupled at the radiation time step, which is about half hour. In the ocean model, we use roughly 1 hour coupling, and that is essentially we explicitly resolve the diurnal cycle in the ocean, so we don't have to necessarily parameterize the diurnal cycle. We have different configurations of the ocean model, not just the global. It can be configured in aquaplanet configurations as shown here, or you can just like, I mean, it's in other models, the MIT GCM, you can put a ridge here, you can do some idealized simulations. We are actually spending more and more time creating out of the box regional configurations of MOM6. This is an example for the Caribbean region. In this case, the boundary conditions come from a global model, and then the grid resolution inside it can be as fine as, I think, I can't remember the grid resolution. This is actually a fine grid resolution within the region of interest. But this is, I believe, 1/12 degree, domain. So we are creating other versions of the regional MOM6 configurations. As I showed yesterday, we do have a biogeochemistry component. That's the MARBLE, Marine Biogeochemistry Library in the Ocean model. Recently expanded it to include micro and mesozooplankton types. And we can run a fish model, feisty ocean fish model offline. We are in the process of incorporating it in a prognostic way within the ocean model. This offers essentially improved estimates of food resources for fish and other higher trophic levels. If you want to learn more about ocean models, you can visit the Ocean Model Working Group. There's also, I mean, we are expanding it now to include also various MOM6 as we switch to MOM6 related sort of details as well. So with that, I'll stop. And if you have any questions, I'll be happy to take them. Thank you. And again, tomorrow we'll be focusing on the parameterizations.
Thanks, Gokhan. Thanks a lot for your talk. Let's thank the speaker. And now, any questions from the offline participants? Please feel free. As you know, you are encouraged to ask questions. So, yes, Shreyashi.
Hello, sir. So I'm Shreyashi. So this is the first time I just got into an extensive ocean modeling, so I have some questions. So the first one is that in one of the slides you talked about Arakawa B grid, and there you wrote that it is used because it takes into account smaller truncation errors in Coriolis term, but larger truncation errors in the pressure gradient term. So why would you consider a smaller truncation error in the Coriolis term, but not in the pressure gradient terms?
Well, that's a good question. I mean, these are coming from sort of traditional methods. It is a trade-off, and it is when certain approximations are done, essentially, you have to live with it. In this case, for example, we did not develop MOM6, POP at NCAR, and it was developed at Los Alamos National Lab. And at that time, the developers actually choose to use those discretizations. And I don't know what their thinking was, but it was just a trade-off, essentially. So at coarse resolution, some of the things may not be mattering that much. But as we get to finer and finer resolutions and equatorial flows, that may matter more. So it is essentially designed by, I guess, I'm not, if I were to design it myself, I'm not sure which way I would go because it's not an easy question to answer.
Does this mean that the choice of the Arakawa C and B grid is also on the same reasoning, that depending upon the objective that?
Right. I mean, when I was a graduate student, actually, I used the Arakawa C grid in my DNS simulations, simply because at that time I was more interested in more accurate calculations of the or easier calculations of the continuity equation. And as I showed, you can compute the continuity equation a lot easier on the Arakawa C grid. But again, it's a trade-off. It's a trade-off.
Thank you, sir.
There is actually a paper by, I think, I can't remember the date, Arakawa 1969 or something. He goes over all of these grids. There's the Arakawa B, Arakawa A, Arakawa C, and they have other properties. So I didn't give you a full complete picture, but if you're interested in, you can take a look at that reference going back to like almost 50 years ago.
Good morning, sir. I am Chitranjan. So very nice talk. You explain everything, beginning from the like governing equation, then discretization, and even up to the CFL condition and tripole errors. Everything you discuss. So one thing I just want you to explain a little more, like what are the role of a coupler? So like coupling models when you are in the ocean setup, your like hydrostatic states are different. When you are in the atmospheric model, you have to consider non-hydrostatic like formulations. Also, some like slow marching variables will become like fast marching variables. So, what are precisely the roles of coupler between the ocean model and atmospheric model? Can you please explain?
Yeah, so just to clarify, we do not use non-hydrostatic in the atmospheric model either. So it's still the hydrostatic formulation because the resolution is still relatively coarse. And so you can think of the coupler as a communicator between the component models. And we pass to the coupler sea surface temperature, for example, and the ocean currents. And the atmospheric model passes, it is winds, it is 10 meter, I believe it's 10 meter air temperature, humidity, and all that stuff. And then coupler, in a sense, uses the bulk formulations to compute the fluxes. Then those fluxes, if they need to be passed on to the ocean model, it passes them to the ocean model. If they need to be passed to the sea ice model, it passes them to the sea ice model. If they need to be repassed to the atmospheric component, then it passes them to the atmospheric component. So then there is a lag between the components. In a sense, what I'm trying to say is that, for example, we run the ocean, let's say atmospheric model runs for 1 hour. It passes the needed states, atmospheric states, and the shortwave radiation, for example, or radiative fluxes to the coupler. Based on that 1 hour time step, let's say, those fluxes are calculated and those fluxes are being passed to the ocean model, then the ocean will run them for 1 hour, let's say. However, during the previous communication interval or coupler interval, ocean also passed to the coupler its SST and surface temperatures. So those are actually used to compute fluxes, for example, for the atmospheric model as well. So there is actually one coupling interval lag between the ocean component and the atmospheric component, let's say. So there's a slight lag between the fluxes. But all of the fluxes are actually calculated in a conservative way, and we do not lose anything that comes from the atmosphere. If the atmosphere is sending us 100 units of whatever fluxes, then ocean, sea ice, and land will properly partition them and will use all 100 units of those fluxes. It's a rather complicated thing. And if you are interested in, we have actually more detailed, I mean, this is a short summary, but how those things are computed, those are all documented and you can actually access them through CSM websites.
Thank you, sir. Thank you.
Any other question? Yeah.
Hello, sir.
Yes.
You have talked about a lot of approximations used in the models, right? So approximations leads to errors, right? So out of these approximations like hydrostatic, Bosnian continuity, and spherical earth, and so on, so which of these approximation leads to the most error in the model, if you were to look at a model development perspective?
So I would not, well, I mean, I'm not sure whether it's error or not, but I mean, as we were mentioning, hydrostatic versus non-hydrostatic, I think as we go to finer horizontal resolution, we need to be also be mindful of the vertical resolution. So with the finer resolution, we need to likely go towards non-hydrostatic formulations. In the atmospheric component, usually that is order, well, I mean, it's still open for debate. Usually it's the 4 to 5 kilometer horizontal resolution range for the hydrostatic versus non-hydrostatic. But some people think that you can still get away with hydrostatic approximation at 4 to 5 kilometers. Probably, I mean, we need to be mindful as we go to higher resolution in the ocean to go to non-hydrostatic version. And in terms of the Businesque, MOM developers actually, MOM should be able to, I think the MOM is able to check, or you can actually use non-Businesque version of MOM. And to my knowledge, when Bob Holberg and others tried it at GFDL, the differences were rather minor. But I don't know what resolution they tried. So there are some errors perhaps associated with that, but I think they are minor. And I think the other sort of approximations like the horizontal components of the Coriolis force, I think those are relatively small errors. They are not really that big. And I think thin shell approximation and all that stuff, they are sort of standard approximations. And I don't think that the errors are going to be that big compared to the radius of the Earth. I think to me, the biggest thing is the hydrostatic versus non-hydrostatic approximations.
Thank you. Thank you, sir.
Okay, if not, let's thank Gokhan once again. And we will have the third and last part of his talk tomorrow again at 9.
Sure. Thank you
Thanks,
very much.
Gokhan.
Yeah.
Have a good night.
Thank you and have a nice day.
Yeah, thanks.